Ever pondered why computer scientists should understand the concept of expectation? This concept is a cornerstone in probability theory, shedding light on the central tendency of a random variable's outcomes. It's particularly relevant when grappling with algorithms, statistical analysis, and machine learning models, where the element of randomness often comes into play. So, whether you're designing a new algorithm, analyzing data, or training a machine learning model, expectation has a vital role to play. In essence, the concept of expectation is a fundamental pillar in computer science. What exactly is this concept of expectation? Imagine you're playing a game of chance. What will you win on average? That's where the expectation of a random variable comes into play. It's a kind of average outcome, taking into account all possible outcomes and their respective probabilities. When we talk about a discrete random variable, think of it as distinct outcomes, like flipping a coin or rolling a die. The expectation, denoted as EX, is calculated as the sum of each outcome multiplied by its probability. On the other hand, a continuous random variable can take any value within a certain range. Think of it as measuring something like height or weight. Here, the expectation is calculated as an integral of the product of each outcome and its probability density. In simpler terms, whether you're flipping a coin, rolling a die, or measuring heights, the expectation is your average outcome, factoring in all possibilities. Hence, the expectation of a random variable is simply the weighted average of all possible outcomes. Expectation has some interesting properties. Let's delve into them. First, linearity. The expectation operator is linear, meaning for constants and random variables. It satisfies the properties of linearity. Second, the constant property. If you have a constant, its expectation is just itself. Lastly, independence. If two random variables are independent, the expectation of their multiplication equals the product of their individual expectations. These properties make expectation a versatile and powerful concept in probability theory. To better grasp the concept of expectation, consider these examples. Imagine a fair coin toss. If we let x equal 1 for heads and 0 for tails, we find that the expectation, or the weighted average of outcomes, is 0.5. Now let's roll a fair six-sided die. We'll let x represent the outcome. In this case, the expectation of x is 3.5. Finally, let's explore a uniformly distributed random variable on an interval from a to b. Here, the expectation of x equals the average of a and b. In each of these scenarios, we've computed the expectation by multiplying each possible outcome by its probability and adding these products together. This provides us with a single value that represents the central tendency, or the most expected outcome, of each random variable. These examples clearly illustrate the computation and interpretation of expectation. In a nutshell, understanding expectation is vital for every computer science student. We've unraveled its importance, concept, properties, and presented examples. These insights are invaluable in dealing with algorithms, statistical analysis, and machine learning, so next time you encounter a random variable, remember to compute its expectation. It could reveal more than you think.